You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. The relatively new and recent GaN technology can operate at very high frequencies. It can also deliver major efficiency gains, making it a powerhouse in the electronics industry. When used with optimized controllers, the wide bandgap material can significantly reduce the size of auxiliary power supply units, or SMPS, including quasi-resonant flyback converters ranging up to 100 watts. In this episode, ST Microelectronics and Worth Electronic experts will cover the basics of flyback converters, as well as introduce you to the most recent GaN-based auxiliary converter designs and their main benefits. We'll also discuss how to reduce the size and improve the characteristics of onboard magnetics and eliminate or reduce the heat sink.
So, as anticipated, we are going today to talk about power supplies with GaN technology up to roughly 100 watt. I introduce briefly myself. My name is Esther Spitale, and I work for ST Microelectronics in the technical marketing field for covering products that are power conversion ICs and GaN transistors, so with specific focus on GaN technology. So at the beginning of our presentation, I am going to show the benefits of GaN in power conversion applications. Then, together with my colleague Radek, we will go more in detail in quasi-resonant flyback topology, which is one of the topologies where GaN technology brings benefit, and this is the focus of today's webinar. And then we will show you also our new family of offline converter, our Viper GaN family, which embeds the GaN switch. So let's start having a look to the benefits of GaN technology in power conversion. In order to understand why GaN technology brings benefits in power conversion applications, we want to start describing some of the physical characteristics of GaN that have this impact. One of the difference between GaN and other power semiconductor technology regards the gate charge. The graph that you see in this slide shows indeed the gate charge versus the voltage of the gate source of the different transistors, and this is shown for three different power transistors technology. So we see in dark blue the standard silicon technology, a very good technology from ST, DM6, one of the newest, silicon carbide technology, and GaN technology in light blue. First of all, we can notice that the gate source voltage of the GaN is limited to roughly 6 volt. This is indeed the value roughly at which it is suitable to be driven at the gate of a GaN transistor. While for silicon, and even more for silicon carbide, this value is higher. The other point that we can notice in this graph is that the gate charge of the GaN transistors, the light blue waveform, is much smaller with respect to the gate charge of the other technologies. If we consider the losses that comes from charging and discharging the gate of the transistors while switching in a power conversion topology, so in an SMPS, in a switching mode power supply, these losses are proportional to the product between the VCC, which is the supply voltage at which the gate of the transistor the gate of the transistors has to reach, and the gate charge. So if we consider this product, we can see that basically if we compare GaN with the other two technologies, silicon and silicon carbide, we see that the GaN has roughly 30 times lower gate charge or product between gate charge and VCC, And this means basically that the losses due to the charging and discharging, the gate charge during the switching cycles is roughly 30 times lower. Of course, this is only one component of the losses, and this is a component that is especially relevant in power conversion applications, so in SMPS, because in SMPS the switching frequencies are typically quite high. Even more important, even a more important characteristic of the GaN technology regards the output capacitance, or better, the energy associated to this output capacitance. So whenever a transistor switch, of course, we need to, again, to charge and discharge not only the gate capacitance, but the output capacitance, which is even more relevant. Also, here in the graph shown in this slide, we compare the EOSS, so the energy associated to the output capacitance, that it's a parameter that we can easily find in the datasheet of all the power transistors, and we compare for three different technologies. Again, in light blue we see the GaN technology, in pink the silicon carbide technology, and in dark blue the silicon technology. So if we this energy is plotted with respect to the voltage, to the drain source voltage, but if we consider the typical bus voltage of 400 volt, we can see that silicon has roughly 2 times higher EOSS with respect to GaN. So if we compare GaN and silicon, GaN has the half of the EOSS. And this is also a parameter that is very important to reduce the overall losses. Last but not least, we want to compare also the reverse recovery charge of 3 different technologies. So this is also a parameter that we can find in the datasheet of power transistor devices. Here we compare GaN, silicon carbide, and silicon. Already we see that the silicon carbide show a reverse recovery charge that is almost 1 order of magnitude lower with respect to the reverse recovery charge of silicon, but GaN has really 0 reverse recovery charge. This parameter is very important in topologies where we have R switching, where basically this charge is dissipated into heat, into losses. Now we want to show where GaN is used, in which topologies GaN technology is used. Of course, we don't show all the topologies, but let's say we show the topologies that today we see in the market more utilizing the GaN technology, because this technology brings benefits in these topologies. We start describing the topologies considering increasing power. So if we consider power supplies for a power below 100 watts, so we talk about some tens of watts, several tens of watts, up to roughly 100. One of the typical topologies used in this kind of power supplies is the quasi-resonant flyback, very used in auxiliary SMPS. This way, the way in which the quasi-resonant flyback work is called zero current switching. Roughly for the same power range, we have an optimized topology called active clamp flyback, where the passive clamp of the standard flyback is substituted by an active clamp. Here we can see there is another transistors in the clamp. And this is a topology that brings benefit of being independently on the technology that we use. This topology brings the benefit of showing higher efficiency. And this is particularly used in chargers or in LED drivers, where it is important to have high efficiency and to switch at very high switching frequency to have, let's say, important power density. If we look at power conversion topologies for higher power range, for instance, the range of some hundred of watts and above, typically we have a DC-DC stage that is very often realized in half-bridge resonant LLC. or let's say here we talk about half bridge. For higher power, we could have even a full bridge, but let's take the typical example of the resonant LLC. This is also a topology where we see GaN is used because it brings some benefits that we will show later in the next slide. And when we talk about this kind of power level, very often there is a PFC in front, and this is why the resonant LLC is called, is a topology used normally as DC-DC, so after a PFC stage. For very low power, or relatively low power for a PFC, so in the range of few hundred watts, typically a boost stage is enough. When we talk about power above 1 kilowatt, one of the very common topology for PFC is a totem pole bridgeless PFC, because let's say when the power starts to be important, like 1, 2, 3 kilowatt, efficiency becomes a key point. And then it is important to find the right topology to ensure the high efficiency. Totem pole PFC is a topology, is also one of the topologies where we see in the market the usage of GaN because it brings benefits. Let's see what are the benefits of GaN in these technologies. Let's start on the right-hand side of the slide. So on the last topology that we saw, the totem pole PFC. Totem pole PFC is a topology that is used to overcome the limitation of standard boost in terms of efficiency when we talk about power of some kilowatt. The topology itself is bridgeless, so avoiding the diode bridge, we have higher efficiency, but it is mandatory to have, as a main transistors here, the pink one, a wide bandgap technology. It could be silicon carbide, it could be also GaN. Here, let's say the usage of a wide bandgap is mandatory. Otherwise, this topology doesn't make sense. The benefits of using a wide bandgap, and particularly GaN in this topology, is the efficiency. So the usage of GaN here is done at purpose of having a very high efficiency. If we look now at the topologies that are in the middle, the active clamp flyback and the resonant LLC, here we talk about topologies where we have 2 GaN switches in half bridge configuration, and we talk about soft switching. In this case, by definition, these topologies are show a very high efficiency. They show a very high efficiency even with using silicon technology. Using GaN in general can bring a bit more efficiency, but this is not the main advantage, I would say, in this kind of topologies. The main advantage here is the possibility, thanks to the fact that the parasitic capacitance, like the output capacitance, are lower, we can switch at higher switching frequency. And the benefit of switching at higher switching frequency consists in the possibility of reducing the magnetics and therefore to increase overall the power density. The last topology, and that is the one that we will show in more details afterwards, is the quasi-resonant flyback. Here again, it's very important to have, it's very crucial, the fact that GaN has very low parasitic capacitances, especially the output capacitance and the energy associated to this output capacitance. And this brings both benefits. So thanks to the fact that the parasitic capacitances are lower, it is possible to increase the switching frequency because the time to charge and discharge this capacitance is lower. But since this topology is not the pure soft switching, it is also very important here the fact that the output capacitance is lower because we can also achieve a much higher efficiency than the one that we would get in a quasi-resonant flyback with silicon. Okay, now I give the word to my colleague Radek, that is going to describe a bit the quasi-resonant flyback topology and to give some, let's say, description of the way of operation of this topology.
Hello also from my side. Let me briefly introduce myself. My name is Radek Sochor, and I work as an application engineer for ST Microelectronics, and I'm focusing on the gallium nitride devices and the low power supplies right now. Now let's talk about the quasi-resonant flyback. Let's go to the basics. First of all, this is the topology of the quasi-resonant flyback. It's the same configuration as the standard flyback converter, just with the different control scheme of the switch itself. From the left, we have an input bridge, then the clamp circuit that consists of the transil and the ultrafast diode, for example. The offline converter, in this case, it can be Viper GaN that we are going to show later. It's a PWM control plus the low side switch. On the secondary side, we have a synchronous rectifier plus the MOSFET to ensure the maximum efficiency of the whole converter and to ensure the maximum power density also. And of course, we need some regulation. We need to control the constant voltage on the output. So we need some constant voltage controller on the secondary side. Let's go to the operation principle of the quasi-resonant flyback. So we are starting at the on phase. So that means the low side switch is switched on. The current is linearly rising with the slope of the primary inductance of the transformer. Voltage on the drain source is given by the current times the RDS on. And the current on the secondary is 0 because right now we are charging the magnetics of the transformer. In the second stage, we are entering the demagnetization phase. So in this time, the current from the secondary is flowing to the output capacitance and to the output load. So we are actually charging the output in this stage. One main thing is the voltage on the drain source. Here is the spike from the leakage inductance, and we have to design around that to limit this voltage not to destroy the low side switch here. After this leakage spike, there are voltage on the drain source that is given by the input voltage plus the reflected voltage from the output. After this, the magnetics are completely discharged, so we don't have any energy inside. And the only thing that's keeping the energy inside is the oscillation between the primary inductance and the capacitance of the switch. So this is this oscillation. This is main difference between the standard fixed frequency flyback and the quasi-resonant operation. It means that we are switching in the volley of the oscillation to ensure the minimum losses with the switching of the on of the transformer, of the transistor. Let's summarize some features. It's a standard flyback topology, so nothing new. It's a transition mode converter. That means we are in the border between the discontinuous conduction mode and the continuous conduction mode. But that means we have to switch at a zero current, so switch at the volley, so we need to sense it somehow. And it means we need to have a variable frequency operation. So the controller needs to change the frequency with the load and with the working conditions. Okay, now we are heading to the main losses. Inside the flyback converter, there are two types, topology related and power switch related. Topology related, that means the parasitics of for example, transformer or the PCB that we can't get rid of even in a good design. We are trying to minimize it, but they are still there. Power switch related, we can change these losses by the switch itself. So if we choose standard MOSFET or gallium nitride, we can change this. Now let's compare the silicon and the gallium nitride here. First of all, on the left side, we can see the standard conduction losses here. It's given by the RMS current and the RDS-on. This typically is only given by the RDS-on, and the gallium nitride here, compared to the silicon, has lower RDS-on. These losses are the switching losses, and actually here we are integrating the COSS and the voltage present on the switch itself times the switching frequency. On this graph, you can see the comparison between the silicon and the gallium nitride with a very similar RDS-on. So we are in the same range. Right now, as you can see, the EOSS is always lower than in the silicon MOSFET type. So we are losing much less power, so we need to dissipate much less heat. Just to be complete, on the right side, there are some topology-related losses. This first is the loss that is from the parasitic capacitances, for example, from the PCB or the transformer. This one is from the leakage inductance, and this one is from when the switch is turned off and the current that is left is generating heat inside the switch. Okay, variable frequency operation. In the quasi-resonant flyback, with the higher input power, we need a different switching frequency. You can see it on this graph. We are at first, we are in the burst mode to have the low standby. After that, frequency foldback mode, so we are rising the frequency and switching in the subsequent volley of the oscillation. In the volley skipping mode, we are reaching the maximum frequency limit, and then we are switching to the other volley. So we are actually skipping 1, 2, 3 volleys, depends on the load. And on the right side, there's actually true quasi-resonant mode. So we are switching at the first volley of the oscillation, and we are decreasing the frequency to get more and more charge into the magnetic circuit of the transformer. From this chart, we can see that the higher losses are at the wide range operation. As you can see, the input voltage rising here. This means the frequency is rising, and from that, the more losses are present. So when you are designing the wide range operation, you need to design for the lowest frequency and for the highest frequency to match the losses that you want. In that, just a quick note, the transformer design has to be done for the lowest frequency. So that means for the minimum input voltage and the maximum output power. Let's look at the benefits of the quasi-resonant zero current switching. So I've picked the example of the switching losses here, and I've picked the capacitances of 100 picofarads and the switching frequency 60 kilohertz. So pretty much standard values for today's converters. We are starting at the continuous conduction mode. So we are switching roughly at 500 volts, and the power loss is 750 milliwatts. And the second case, I picked somewhat random case, somewhat average case for the fixed frequency flyback. So we are switching right in the middle of the oscillation at 300 volts, and we have 270 milliwatts of losses. So that means 64% reduction. But right now, we are going to do what the quasi-resonant zero current switching means. So we are switching at the lowest possible voltage. So we are switching at the volley of this oscillation. We are switching at 100 volts, and the power that is dissipated is only 30 milliwatts. So 6% reduction compared to the first case. Now I'm going to give the word back to Esther for some slides about the new Viper GaN family.
Thanks, Radek. So now we are going to talk about ST's new family of offline converter, Viper GaN. As you can guess from the name, we embed here a GaN switch. The slides that you are seeing now shows today's Viper family, and I would say also slightly something that is coming at the beginning of during this year, let's say during 2024. So we have a lot of different offline converters able to target power in flyback roughly up to 20 watts, so 18-20 watt in wide input voltage range. And from in the left-hand side of the slides, we have devices that are able to work also in topologies like buck booster, flyback in primary side. And on the right-hand side of the slides, we have devices dedicated to secondary side, flyback in secondary side regulation. The direction of ST was to have devices with embedded MOSFET able to work at higher power. Viper GaN family is indeed a family of devices that target flyback for 50, 65, 75 watt. As you can guess from the name, as I said, we are talking about an offline converter with embedded GaN HEMT switch. The breakdown voltage of the GaN switch 650 volt, but it's very important to highlight that here we are not talking about a value at which the device breaks. So if we exceed the 650 volt for a very short time, the device doesn't break. And indeed, it is specified in our datasheet that it is possible to withstand even 850 volt for a time of 1 microsecond. The controller, the PWM controller inside the Viper GaN is a PWM controller realized in a BCD technology in order to offer the most advanced feature and the full flexibility that BCD technology can offer. Particularly, we refer to the PWM controller inside the Viper GaN as a sort of advanced quasi-resonant. So the main principle is the quasi-resonant mode of operation, but we embedded several features that will be shown by my colleague Radek later on in order to increase the efficiency in all the input and loading condition, and also, let's say, to manage properly features like the variability of the frequency in a standard quasi-resonant topology in the best way, again, in all the input and loading conditions. In terms of switching frequency, the controller can go up to 240 kilohertz plus an additional frequency jittering that is implemented in order to decrease, to improve the EMI behavior. 240 kilohertz indeed is a frequency that is higher with respect to the typical frequencies that are used in offline power supplies with silicon. The Viper GaN family consists today in 3 devices. We have Viper GaN 50, 65, and 100. The table that you see on the left hand side of the slide in the bottom part shows the power level that is possible to achieve for the different devices, either in wide input voltage range or in European range only. in wide, of course, because the critical case is represented by the minimum input voltage. So for Viper GaN 50, we can reach 50 watt in wide input voltage range, and of course more when we talk about European range only. For Viper GaN 65, we can achieve 65 watt in wide input voltage range. Normally, when we exceed the 75 watt, at least in consumer application, it is possible to, let's say, the flyback itself doesn't see the mains voltage, because a PFC stage is required in front. For this reason, basically, for the flyback, it's the same as the mains voltage is a wide or European only. So in this case, we can say that Viper GaN 100 can achieve 100 watt in case of wide input voltage range. But to be fair, if we consider the flyback standalone, we can say that Viper GaN 100 can achieve 75 watt in wide input voltage range. We have today 4 boards available for the 3 part numbers. For all of them, we have a USB PD charger, offline USB PD charger, because of course GaN technology is already extremely spread inside the charger market. This is clear because in this market it is very important to have high efficiency, but to have especially a very high power density, so to have small and light chargers. But the GaN technology is starting to be used also in many other markets, also in the industrial market and also in the standard power supplies. For this reason, we have available today a flyback board in 50 watt flyback board, and we have in development also other flyback board for higher power. Just a short comment about our evaluation board. If we look at our, on the left-hand side of the slide, if we look at our quasi-resonant flyback board for 50 watt, we see that the peak efficiency is 92.2%. And this is a very high value for a single switch flyback, a quasi-resonant flyback. So we talk about roughly 2 points of efficiency more than same topologies realized with the silicon. Another important point that we would like to highlight is that despite switching at high switching frequency, and despite being a very, very small board with very small form factor, we see that basically the boards remain very cold. So if we look at the temperature of the various components, basically the highest temperature that we get is in the bridge. All the rest stays below the 80 degrees. For 65 watt power supplies, we have today, as I said, a board that is an offline USB PD charger. But very interesting is to see also the efficiency curves of this board. We achieve a peak efficiency 93.5%. So basically between 93 and 94%, again, as an amazing value for a quasi-resonant flyback. Okay, so now I give again the words to my colleague Radek.
Right now we are going to look at the difference between the hemmed gallium nitride and the MOSFET structure itself. On the right side, you can see standard superjunction MOSFET. So that means drain electrode, then the channel that is current flowing through, and the source of the device. Mainly, we are going to focus on the cooling of the device. So the cooling of the superjunction MOSFET is done via the drain electrode, and the main heat is generated here in the channel, so it needs to flow this way. In a hemmed gallium nitride, you actually have a lateral structure, so the heat is generated inside this display, and you can connect the substrate to actual source of the device, and then you create a much more cooling surface for the whole device. So the GaN brings the benefit of a simplified package. It brings better thermal performances because you have bigger area of the cooling, and it brings the simplified PCB design because it is connected to the ground. Now we are going to look at how it is in the real application. On the left side, it's a gallium nitride BiPer-GaN board. As you can see, this big plane is connected to the ground, and it serves as a cooling pad for the device. So you can pretty much stretch it out as far as you want because it's a ground potential. On the other hand, in the MOSFET-based chip, here is the cooling pad. It has to be much smaller because of the EMI, because this plane is actually oscillating between the 0 and the V-in voltage plus the reflected voltage. So you need to make sure that the EMI is right in this context. Here, you can pretty much stretch it out. Okay, and now we are going to look at why is it called the advanced quasi-resonant. And two main features is dynamic blanking time and Wally synchronization. First, let's look at how it is connected. It's connected by just two resistors to the auxiliary winding, by the small two SMD resistors. It's really easy to connect, and you can switch between these easily by the design. Okay, now the challenges of the high frequency operation. I've picked two examples, one with the RM8 core and one with the RM10 core. You can see the calculated characteristics here with the dedicated switching frequency and the input power of the converters. Benefits of the higher frequency operations, of course, is the reduced in the magnetics. So you can actually use smaller magnetics to deliver the same power. The other thing that's almost always forgotten is that you can use lower capacitor values. So for the higher frequency, you need lower capacitor values, so your design can be smaller in this way. As I said before, the higher frequency brings the size reduction. So in this case, roughly 50% in the size. But there are some challenges. One challenge is to maintain high efficiency. So we need to maintain high efficiency at the high switching frequency, mainly due to the switching losses. So again, low switching losses. With the RM10 core, in this example, we can save 2.5 times more switching losses. So we can really switch faster with the bigger magnetics here. And one challenge that I'm not going to talk about today is of course, EMI. With the higher frequency operation, always the EMI is more challenging. Okay, dynamic blanking time feature. It's the feature that brings the frequency change with the higher input voltage. Simply, it switches between the volleys, so it skips the valley with the higher input voltage. So this here it jumps to the other volley, here it jumps to the other volley, and this feature brings the advantage of the lower switching losses with the higher input voltage. So the improvements from this is the balanced switching losses across all of the input voltages. You can design actually smaller transformers because you have a narrower frequency band. Same reason for the less EMI issues. And it's easy to implement because you are adding just two small SMD resistors. Now to the Wally synchronization feature. On the left side, we switch it off in one of our demonstration boards. And as you can see, we are switching too soon. We are switching not in the right volley. As you can see here, it's when we skip one volley, we actually should be switching here. When we implemented the synchronization, we get the switching at the 80 volts lower with the 960 nanoseconds of the delay. What it brings the efficiency improvement because of the lower VDS switching, easy optimization of the design, because it's only done by the voltage on one of the pins of the chip itself, and it's settable just by one resistor. Okay, now I'm going to switch to the video from one of our colleagues. He unfortunately can't be there today, but he prepared one video with some sort of live demonstration about the Viper GaN itself, and he will show you the real measurement on the Viper GaN and on the fixed frequency flybacks.
In this section, I will introduce you Viper GaN in some real measurements, in sort of live demo. For this purpose, I prepared two demo boards. One is a sort of standard Stevel ISA 211 set for the fixed frequency. And the second one is the same type of board, but you can see that instead of the controller and standard MOSFET here, there's some sub-module with the Viper GaN. And I choose this board because this can be set for the very pure fixed frequency without any jitter. And the second one is quasi-resonant with the Viper GaN, so we can see the actual benefits of the quasi-resonant and the whole control unit of the Viper GaN compared to the fixed frequency. This is the fixed frequency board, and I'm using DC power supply, so it's pretty stable and no changes among the pulses. The yellow trace is the drain source voltage, and the orange one is the primary current of the transformer and also of the primary MOSFET, so the drain current. You can see if I'm adjusting the voltage, both on time and off time changes. I just changed the scale so you can see it slightly better. And one more important point is this turn on point. See, the frequency is pretty stable, around 52 kilohertz. And I'm going to change the load again. You can see it. Here, the on time is longer as the peak current is higher, and it's the same with the off time. And this turn on point changes to this proportionally. And it's not just, of course, with the load, but also with voltage. Right now, I'm reducing it, so off time is still the same, but it's on time which changes because the slope of the drain current changes as well, proportional to the input voltage. And let's see the situation at the maximum input voltage. If I disconnect the load, you can pretty much see the simplified trace over here. Here is the rectified input voltage, or as I use the DC power supply, it's 330 volts. And now, again, adjusting the load. So the turn on point would be in the volley. And let me just zoom in so you can see this better. Because usually with higher input voltage, the switching losses, the capacity losses, let's say dissipation, the COSS of the MOSFET are increasing as well. So you could see that right now I'm at approximately 200 volts. So if I change the input voltage, you can see it now. So the peak drain voltage is lower. Right now I'm supplying from approximately 160 volt. And you can see that the turn on point is at the peak of the oscillation. So approximately right now 430 volt. So it is a sort of paradox that at a lower input voltage, the capacitive losses are higher because the turn on point is at the peak. And of course, if I change the load, you can see that it changes again as well. But notice one more thing. Here on the drain current, there is some sort of ringing proportional to the peak or volley of the oscillation, and it is because of the dissipation of the energy in the COSS. So you can see that in the volley is actually lower even at the current. Right now, again at the peak, the oscillation here is much bigger than before. Now let's see the board with the Viper GaN. And you can see quite clearly that it is not that simple as before, because there is some jitter of the fundamental frequency to reduce the EMI. But still we are in pure quasi-resonant mode, so as soon as one cycle ends, another one begins. So right now with this input voltage, which is approximately 200 volt and the 1 ampere load, the switching frequency is 155 kilohertz. Right now I'm increasing the load. You can see it from the peak drain current. The frequency is lower. It's around 100 kilohertz. Yes. So back again with the load to the 1 ampere, and you will see that it is similar with the voltage. I will show that, yes, I'm back at the 155 kilohertz. This is pretty much given. Now reducing the input voltage, you can see it again quite clearly, and the switching frequency goes down, and with increasing input voltage, it goes up again. And you can see I have some ringing of the oscillation here, and I will come back to that later. But right now I'm back at the 220 volt DC of the input, and I will show you something more different and more complicated than the oscillation. And I will need 2 more channels for that, so let me just enable that. Yes, right now we can see the channel 2, the blue one, is voltage applied to the TB pin during the off time. I made some workaround on the module for this, and the red one is the ZCD pin, the zero current detection for the trigger. I will zoom in, yes, and what I will focus on is this delay. Here is the triggering point of the ZCD below zero, and here is the turn on point of the next cycle. And you can see that right now this delay is approximately 160 nanoseconds. The point is that I can actually adjust the voltage applied during the turn, the T off, the blue one. We'll see I'm all about is this curve. You can see that I'm changing the voltage, and also the turn on point changes. I'm actually adding some delay, so the turn on point is no longer in the volley, but with the increased delay it could be at the peak. So right now I increase that, and the delay is approximately 960 nanoseconds. So the turn on point is no longer at the volley but at the peak. Reducing back again. So you can see with the blue curve, this works very well. And what is the point of this? I will show you in the next slide, but good thing about these changes is that if I zoom out, you could see that this is pretty stable, for instance with the load and also with the voltage. Right now I'm increasing the load and now decreasing, and you see decreasing even with the, let's say, volley skipping, and as there are still some volleys and another triggers of the ZCD, the turn on point is still at the same point of the volley, the lowest possible point if I set this delay properly. My point is perfectly visible on this example, because what we call the capacitive losses, it means the energy stored inside all the parasitic capacitances goes with the square of the actual voltage of the turn on point times the switching frequency. And because of the square curve, the reduction if we turn at the peak or in the middle or at the volley is quite huge, with a parasitic capacitance of 100 picofarads, it's a 96% reduction. And here is the example. The turn-on point is in the volley, and I will switch for the peak now. And you can see here in this square, it's the Viper GaN, that the, let's say, thermal shock was pretty fast. And it's still heating, but the temperature of the box up here, it's still the same. Here is the peak clamp circuit, and it haven't changed a bit because I haven't increased the load. What I have done was just increase the delay with the blue curve so I moved the turn-on point from here, from the volley, here to the peak. You can see that the temperature is pretty close to the 70 degrees, so approximately 20 degrees Celsius higher than before when I was in the volley. So I will go back there again now. Again, you can see very quick response. And what I will do next is increase the load, so you can see it here on the top box. So the purpose of this is, right now the temperature of the Viper GaN is 50 degrees and increasing the load now. See, the transils are heating up, but the temperature of the Viper GaN is still roughly the same. Before it was 50 degrees, now it's 51 approximately. Why am I doing this test again? If I go back to the peak, then the additional heat would worsen the RDS on. So going to the peak now, yes, it's heating up again very quickly. The response is very good on Viper GaN. And you can see that I'm very fast at the roughly 70 degrees. Yes. And the temperature is still rising. And yes, it is at higher load, but when I was in the volley, the temperature of the Viper GaN was still the same. But now, when the turn-on point is at the peak, it worsens the RDS on, so it is even higher, 75 degrees. So going back to the volley, yes, quick response, and you can see that the transils are still at the high temperature. And to reduce the capacitive losses even more, there is one more feature of the Viper GaN. You can see that I'm now again in pure quasi-resonant mode. The load is 1 ampere, and right now I'm operating at approximately 130 kilohertz. Now I'm increasing the voltage step by step, the input voltage. So you can see that if the load is still the same, with each step the frequency goes up and up again. But now I'm in what is called the volley skipping region. So the frequency jumps up and down because of the jitter, but right now you can see that the frequency is no longer higher again, but at 148 kilohertz. And increasing the input voltage further, I believe any second, yes, you can see the third volley starts appearing, yes, trying to catch it. And what am I all about is this slope of what is called the TB current, the current to the TB pin. And this, let's say, reduces the frequency limit with input voltage. So now, with the highest possible input voltage, the frequency is no longer higher, but 132 kilohertz, opposed to the 168, I believe, previously. So on this curve, I actually jumped one volley and even now the second.
So welcome everyone from my side. My name is Isaac Wilsat, working as a product definition engineer at Verti Electronic, supporting semiconductor manufacturers with passive components and technical support for realizing new products and reference designs. And today we'll be talking about a transformer characterization in a flyback converter. And as you can see, we will have in our agenda today the impact of wide bandgap material on the magnetics, what kind of parasitics that we can see while designing a flyback converter, and what are the design requirements for a flyback. As well, when we are talking about the wide bandgap and higher frequency, we need to take care of the EMC, and we will see also some tips and tricks how to optimize the design of the flyback transformer for EMC improvement. And last but not least, we will take a look on some designs that have been developed with Viber GaN family, and a conclusion about the presentation. And after that, we can start with the Q&A session. So when we are talking about wide bandgap, whether gallium nitride or silicon carbide, they have, of course, compared to silicon, a higher band gap, which enables them to work at higher frequencies. As well, due to the higher electromobility, it also have a higher breakdown voltage and lower RDS on. So when we say that we can increase the frequency, we are also expecting to decrease the magnetics being used. However, that could be challenging for the magnetics, since decreasing the size of the magnetics can mitigate some EMI problems. There are some parasitics which become more dominant when it comes to higher frequency, such as the parasitic capacitance and inductances in the transformer, which can cause ringing, voltage spikes, or even higher core losses. So when we are talking about the flyback transformer design, or a transformer design generally, we need to have some considerations. So for an LLC transformer design, as an example, we don't really care a lot about the leakage inductance in the transformer. It's even more beneficial to have higher leakage inductance in LLC transformers, so that we can integrate the resonant inductor in the transformer itself. However, for the flyback transformer, we need to keep the leakage inductance as low as possible. And of course, there are more parasitics that we can see also here that can impact the switching on losses. So one of them is the gate charge of the switch being used. And since we are using GaN, they have almost nothing compared to normal silicon. And then comes the second impact on the losses, which is the parasitic capacitance of the primary inductance in the transformer. So of course, we need to keep all of them as low as possible, so that also we can get the benefit from using GaN devices for our flyback converter design. And as I said, for the leakage inductance, it's also a problematic, because during the turn-off phase, the energy stored in this leakage inductance can be dissipated abruptly in the switch or the GaN switch, which might destroy it. That's why sometimes we need to use an external snubber circuit to decrease this effect. And generally, that would bring more complexity and more component count to the circuit of the flyback converter. So our main goal is, of course, to decrease the leakage inductance being used. Coming to the design requirements of the flyback converter, taking in consideration an E-core to be used for this design. And as we can see, the energy being stored in the E-core is dependent on the volume and the permeability of the core itself. So in order to increase the energy being stored, since the flyback converter is mainly about storing energy, and we are transferring energy from the primary side to the secondary side in different phases. So we have the possibility to increase the energy by increasing the volume, which would not be so beneficial for our design since we are trying to decrease the main or the whole volume or the whole area of this design. The second possibility is, of course, decreasing the permeability of the core, and that can be achieved by adding an air gap to this core being used. So there is two possibilities how we can add this air gap, whether we put it on the 3 legs of the E-core being used, or only adding it to the middle leg. For better manufacturability and also for avoiding any EMI problems that can come out by having this air gap on the outer legs, it's preferred to have the air gap in the middle leg only. However, introducing an air gap comes with a drawback, which is, of course, decreasing the saturation current. It's very important to keep in mind what is the saturation current being achieved, and this should be much higher than the primary current on the transformer to avoid the saturation of the core. While starting the circuitry, we have also the problem of inrush currents that can appear, which in most cases are higher than the limit of the saturation current. So we need also to consider these inrush currents in the start of the design. So whether we can design our saturation limit a little bit higher to prevent the transformer from saturating. Another option is, of course, which comes with the new GaN switches, is a soft start option that can be implemented in the circuitry to decrease the inrush current introduced in the circuitry during the start. The only drawback that we will have a bit of delay while having this soft start option, and also we can increase the component count being used for the design. The saturation current is defined by every manufacturer differently, so it's always recommended to take a look on the datasheet how the saturation current is defined. And as you can see here in one of our data sheets, we define our saturation current at 20% roll-off from the initial value, and it can also be a higher or lower percentage of the roll-off. So that's something to take care about while reading the datasheet. Talking about different core materials and using wide bandgap material, we need also to have the material that would fit for our design for high frequency. So in the GaN applications, we decided to go with manganese zinc because it's an available core material, easy to manufacture, and also have a very good behavior up to 1 megahertz, which will cover all the GaN applications right now in the market. Since we already mentioned that the leakage inductance is causing a lot of pain in the circuitry, we can see here that due to the storage of the energy in the leakage inductance during the off phase, we can see these oscillations that caused by the leakage inductance. So we try in our design to keep the leakage inductance below 5% of the nominal inductance value, even less in some cases. To better understand the leakage inductance, we can take a look on this structure, solenoid structure with a symmetrical turn ratio. And in the formula, we can see that the leakage inductance is dependent on many parameters that we can still adjust to have lower leakage. Of course, we can take the insulation area, which is dependent on the insulation material, and 1/3 of the primary winding here represented in red, and 1/3 of the secondary winding here represented in blue, and the green area is the insulation area. By decreasing this insulation area, we can also decrease the leakage inductance, or also we have the possibility to increase the length of the solenoid to decrease the leakage inductance. So here we can see it in practical or a better visible way that in this design, we have on the left side the best design where we have a flat coil with a short average distance, a longer length, which can, of course, have a great impact on the leakage inductance. So it will be much less than the second and third design where we see it's more compact, but having a lot of windings stacked over each other. In some cases, we also need to add some shelves to meet some safety requirements. So it's always a challenge to make the trade-off for the design between leakage inductance and the compactness of the transformer. Another technique which improves the leakage inductance by almost 25% is the so-called sandwich technique. So as you can see here on the right side, that the primary winding is being winded, then an insulation material is being added, starting winding with the secondary one, and then insulating it, and then one more time adding the rest of the primary winding. Of course, that's a very good technique for leakage inductance, but it comes, of course, with more winding labor and a higher cost. Since we are talking about higher frequencies, so something very important when considering high frequency is the AC resistance inside the transformer. And of course, it plays a role in the CCM mode, but also has a high importance in the DCM mode of operation, since we have higher peaks. And we can see it here in the diagram, the primary current represented in red and the secondary current represented in green. By applying a sawtooth waveform and doing an FFT of this waveform, we can see that we have the frequency plus the harmonics that are visible here, which have also a big impact on the AC resistance in our transformer design. Here also another diagram showing the relationship between the increase in the AC resistance and the thickness of the wire being used in the transformer winding. And we can see also that the AC resistance gets very or exponentially high when we increase the thickness of the wire being used. So there are some effects that come out also with a higher frequency, like the proximity effect or the skin effect. Here there are two different effects that impact also the efficiency and the losses of AC. So for the skin depth, of course, if the induced eddy currents use high frequency, the real diameter being used by the wire gets smaller than the actual size. And also for the proximity effect, we can see this effect between two adjacent wires, whether the current flowing in the same direction or in opposite direction, the current will, or these eddy currents will generate currents flowing away from each other, or also close to each other, will not be using the whole diameter of the wire being used. For modeling the AC resistance, there are also some analytical or theoretical models that can be used, which are highly complex and time-consuming. That's why most of the time we go for 2D or 3D modeling using ANSYS Maxwell to have a better calculation of the AC resistance at the desired frequency. Another solution, as we have seen, to decrease these proximity and skin effects coming out with a high frequency, we can use, instead of a solid wire, a Litz wire. So a Litz wire is mainly a strand of small wires together that form the bigger wire that we need. And of course, if we have the smaller diameter in this case, then we will have less skin effect and also a proximity effect. Here we can see a comparison for a DCM topology at 100 kilohertz with 230 volt input and the same load condition 30 watts between a solid wire and a Litz wire transformer. We can see here that the temperature goes up to 100 degrees Celsius. And on the other side, while using the Litz wire, we have temperature of around 65 degrees Celsius. So we see the great impact on the AC losses while using the Litz wire. What kind of EMC considerations can we take care of while designing the transformer? Since we have in our flyback topology a lot of parasitics that can contribute and create common mode noise that couples to the earth and come back through the line. So we can see here the parasitic capacitance of between the primary and secondary windings. They can couple into the secondary of the circuit, or even the capacitance of the switching MOSFET or GaN FET can also contribute some common mode noise into the circuitry. And of course, we need to keep these loops as small as possible to avoid any EMC problems. So for the transformer design, what kind of EMC considerations we can do? We have a couple of options that we can use. First, of course, is adding a shielding. So we have the option to add a shield between the primary and the secondary winding and grounding this shield, which will prevent this common mode noise to couple into the secondary winding. Or we can also add a grounded flux band on the outer side of the transformer and grounding it to ground any kind of noise that can come from the transformer. Also, there is a more option, which is a core grounding to also have smaller loops when it comes to common mode noise. Another technique is a cancellation technique. It can happen by introducing an auxiliary power supply, auxiliary winding to the transformer design, and which will also have a negative polarity to the primary winding to cancel the common mode noise. And we will have also a look on the next slide on it. Of course, while designing power topology, it's always important to use filters. So an EMI filter is always recommended while designing power to have smaller loops for the common mode noise and also differential mode noise that can come out while using the circuitry. So here we can see by adding a shield, so it's a thin layer shield of one turn winding that can be put between the primary and the secondary. And while grounding it, we can see here if we have a common mode noise or a noise source coming from the primary, a very small amount will be translated to the secondary side, and that's what we are trying to achieve. It is important to bear in mind that this winding or this shield should be very thin, thinner than 50 micrometer, because between the primary and the secondary winding we have high eddy currents, which can cause a lot of losses with increasing frequency. So the cancellation or balance, as we already mentioned, we can add an auxiliary winding to our transformer design with a reverse polarity to the primary winding to cancel the common mode noise coming from the primary side, so that we have in the end a zero noise ideally. For this auxiliary or the cancellation technique, we need to use whether a discrete external capacitor to inject these common mode currents in the opposite direction of the currents coming from the primary side, or we also can make use of the auxiliary capacitor or the parasitic capacitance from the auxiliary winding to induce these currents in the opposite direction. Now we are getting a look about some designs that has been made in collaboration with Würth Electronic and ST Microelectronics. These reference designs using the Viper GaN families for different power levels. And as we can see here on the transformer, on the top transformers, we have here extended rails. They are mainly being used because of safety standards. For a higher power, then we have also this transformer with flying leads. However, it is not recommended to have such long flying leads since they also act as natural antennas and can cause a lot of EMI problems. Now we can take a look on the data sheets and the electrical diagrams of these transformers. You can see also always in the data sheet the leakage inductance stated in comparison to the main inductance, and we can see here that the inductance or the leakage inductance is 2%, which is very good for the design. Also in the electrical diagram of the transformer, we can see that there is a shield in both transformers where they can be grounded also to decrease EMC problems. And this is the transformer with a flying lead. We can see also that the leakage inductance is kept very low, and also it is important to take a look on the saturation current to make sure it's higher than the current being used in the primary winding. So a final conclusion out of this presentation that we have already seen that the flyback transformers, it's mainly about storing energy. That's why we need to introduce an air gap, since the energy is not transferred directly during the on time. And we have seen as well that the structure, the winding way, and the tips and or the tricks that can be made to decrease the leakage inductance while designing the transformer. And since we are always introducing an air gap, we need to think that we should keep the saturation current higher than our current being used, and also make sure that the inrush currents don't lead to saturating the transformer. With high frequencies, of course, we have seen that the AC resistance become very dominant. So we have seen also some techniques to decrease these AC resistance, especially the proximity and skin effect that appear with higher frequencies. Decreasing EMI in the design of the transformer is also possible. We have seen the shielding, we have seen the cancellation technique, and also, as I said, for power topology, it's always recommended to use an EMI filter.
To download the slides from today's presentation, simply click the link in the description or visit Würth Electronic Video Center at www.we-online.com/podcast. While you're there, you can also check out the entire lineup of flyback transformers, custom transformers, and download GaN-based converter designs at www.we-online.com. We understand that some videos and images are not available on all streaming networks. To replay the entire podcast with video, please visit our website at www.we-online.com/podcast or check out the Würth Electronic YouTube page. You are listening to Würth Electronics What's Up Radio Podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Electronics What's Up Podcast.